Okay, so here we have the May 2018 paper 3 for time zone 1. And again, we're focusing on part A, section A. And then section B is the optional topics, which of course we're doing astrophysics. We'll get back to that. But let's proceed to section A. And so here we have the first question, and it makes reference to a magnetized needle that is oscillating in a magnetic field. And it tells us that the time for 10 oscillations is recorded. And then we have a graph here of that time for 10 oscillations as the dependent variable, and then the independent variable set by the experimenter is the magnetic field measured in Tesla. So we have some data points with error bars, and it says that the uncertainty in the magnetic field strength is negligible, so the error bars do not show. So first we have number 1A, which says draw on the graph a line of best fit for the data, and we can see that this is curved. We should attempt to, with our curve, hit all of the data points, I suppose. I think that's possible. And just try and draw one straight curve all the way through. I'm sorry, I used the word straight. Draw a curve all the way through. Curves are not straight. Here we go, not too shabby. This continues on the following page. So we have BI. Write down the time for one oscillation when B is 0.005. Include the absolute uncertainty. So there's 0.005 Tesla, and I found the data point. It appears the data point falls somewhere around 8.4 seconds for 10 oscillations. And if you look carefully, I don't think there's any way for me to pinch zoom this, but if you look carefully at the error bars, they are not one square, but it looks like maybe 1.5 squares, where each square is 0.2 seconds. So it appears based on the error bar that the uncertainty in the time is 0.3 seconds for 10 oscillations. So yeah, based on the graph, we can see that the time for 10 oscillations where the magnetic field is 0.005 Tesla is 8.4 plus or minus 0.3 seconds. So we want the time for one oscillation, so we're going to divide by 10. 10 has no uncertainty, it's just a, I forget what they call it, it's an exact number. So when you divide a number with absolute uncertainty by an exact number, you divide both the number and the uncertainty. So that sounds like a mouthful. Let me just show you what I'm talking about. So 0.84 divided by 10 is 0.84, so that'd be 0.84 seconds plus or minus 0.03 seconds for absolute uncertainty. All right, let's proceed. Double I. We have a relationship here that the period is given by some constant over the square root of the magnetic field strength in Tesla, where K is a constant. So it says find the value of K when B is 0.005 Tesla. So then we also know what P is. That was BI. We just figured that out. And it says state the uncertainty in K. All right, let's go. So again, B does not, the magnetic field does not have an uncertainty. The uncertainty is negligible. So we're multiplying the period and its absolute uncertainty times an exact number. So that 0.005 is being multiplied by 0.84 and also is applying to the 0.03. So 0.84 times radical 0.005 gives us 0.059. So 0.059 plus or minus 0.002. And it's like 0.0059. What are the units? Well, that's actually triple I down on the bottom. State the unit of K. Period is in seconds, and magnetic field strength is in Tesla, but that's radical B, so that gives us units of seconds times Tesla to the 1/2. I'm itching not writing the units up top here. And there we have it. Let's see if there's more to this question. Indeed, there is. So we're plotting period squared versus 1 over magnetic field strength. So C says, sketch the shape if you were to plot period squared versus 1 over B. So the original expression is already given right here. Period is K over radical B. So let's see what happens when you square the period. That would be squaring both sides. So when we square both sides, we get rid of the radical on that magnetic field. But that's still an inverse relationship between period squared and and magnetic field. There go Miss Coleman's bells. And that's not what's being plotted. You would get an inverse relationship if you were squaring period squared versus magnetic field strength. But what the student is plotting is period squared versus 1 over magnetic field strength. So let's rewrite the expression to match. So then there we have period squared versus 1 over b, and you may recognize that this takes the form of a linear relationship. And not just linear, but also directly proportional, because on the equation of a line, y equals mx plus b, there is no plus b here, therefore b must be 0. And so we have a linear relationship with a y-intercept of 0. That is direct proportion. And there we go. Made a little thing down here. Now, my layout right here, over there, here on the side, this stuff over here is not actually needed in order to solve the problem. The 2 points are the fact that the line is linear and the fact that it passes through the origin. It says sketch, it does not say sketch and explain. Now, what about the constant? Is there anything about the slope? I bet there's a follow-up. State how the value of k can be obtained from the graph. Ding, ding, ding. So the slope would be the k squared, the constant squared. So if you took the slope and then took the square root of the slope, that would give you the value of the constant. Sometimes they want you to solve for the constant, but nope, not this time. Next question. Circuit question. So we're trying to find the internal resistance of a cell of known EMF. Remember, EMF, electromotive force, is measured in volts. And again, EMF does not change, but the terminal voltage across the battery does, and that's because there's a voltage loss because of the internal resistance of the cell, and that's what they're trying to figure out. We have an ammeter. I'm assuming that's a perfect ammeter with no resistance. And we have a 10 ohm resistor. So it says draw a circuit diagram that would work. So, I mean, ammeters are connected in series. There's only one element here, circuit element, the 10 ohm resistor. So this is a very basic question. Here's our circuit. Use the symbols as provided. I don't know what else you can say about that. So next question. So this is an interesting question. It says that the resistor gets warmer, and how is that going to affect the calculated value of the internal resistance? Just be careful reading here. The resistor getting warmer isn't going to affect the actual internal resistance, but it will affect the calculation. It's going to introduce an error. So the 10 ohm resistor getting warmer will increase its own resistance. So that's the first point of 3. Temperature goes up, the resistance of the 10 ohm resistor goes up. You must recognize that. So since we're looking at the internal resistance, we know that the equation for internal resistance and EMF is given in topic 5.3. So then we know the value of the EMF. This is a known EMF, that's known. And then the current is going to be measured. But the thing is that I think the design of the experiment was that the resistance of the 10 ohm resistor was going to be held constant. Or not held constant, but it was going to be fixed. It's assumed to be 10 ohms. But if the temperature increases, then that value of R is going to be greater than 10 ohms. Okay, so electromotive force is the current times the sum of the resistance plus the internal resistance. But the internal resistance is making reference to the cell, not making reference to anything that might be happening with the fixed resistor, which is actually not fixed because as it heats up, that R value, the capital R value, is going to increase. Since that's going to increase the R plus R, and if that is increasing, if that portion is increasing, this part is increasing, then that means that for a fixed electromotive force, then the actual current is going to be decreasing. So in other words, that's what I wrote here. Actual current reading is therefore less than if the resistance of that resistor, the 10 ohm resistor, were assumed to be 10 ohms. And point is, and this is why this is in topic A, is that if the experimenter did not recognize or control for the heating of the resistor, and the experimenter just said, oh yeah, the attached resistance is 10 ohms, then that's going to cause a lower current reading, and then the sum of the resistor and the internal resistance is going to be higher. Therefore, what happens is that the calculated resistance, which they actually get out of the equation, is going to be greater than the actual internal resistance in the circuit. And so the 3 points here, the first point is as temperature of the 10 ohm resistor increases, the resistance of the 10 ohm resistor goes up. That's point number 1. The second point is as a result of that and using this expression, that means the actual current is going to be less. That's point number 2. And if the current reading is less, then what happens in the end as a result of the calculation is that the calculated resistance will be greater than the actual resistance. And there's our third point. Again, the intent of this question is that what would happen to the calculated value of the internal resistance if the experimenter did not acknowledge the heating effects of that internal of the attached supposedly fixed resistor. Now that could also be considered a random error if you have no way of controlling for that the heating effect of the fixed resistor. Then then what are you going to do? And so C actually gets to, when I say, what can you do? C actually asks, well, what can you do? So one solution is always to take more data and is to take, Fitz is laughing, is to take more data, which is true, but it's not just take more data. You can actually take more data by using a variable resistance as they advise, and then in so doing, you can actually make a graph, kind of like a voltage current graph, and use the gradient to figure out the resistance. But let's get a little more specific. Now, when I talk about a voltage current graph, you could say like, well, they didn't mention a voltmeter, and there's no voltage in the expression, but there kind of is. So let's actually expand out this expression for the EMF. And you can actually rewrite this expression where the total current and the total resistance of the circuit is what's known as the terminal voltage. And I'll show you what I mean by that. So this cell right here actually includes an internal resistance. Sorry, that's the Regents version. I've used as like a little box, but there's an internal resistance in that cell. And so the actual, without the internal resistance, the voltage that comes out of a battery, that's the EMF. That is the perfect battery. If there's no internal resistance, technically it's like what you would get from a fresh battery, but even a fresh battery has some internal resistance, and then as time goes on, the internal resistance increases. At any rate, if you were to measure the voltage across these 2 points right here, that right there is going to be, you can call that the total voltage. It's also the terminal voltage. It also happens to be the voltage not just across the battery, including the internal resistance, but it's also the voltage across the circuit element down here, across that resistor. Again, we're assuming that the ammeter is ideal and has no resistance or voltage impact. All right. That being said, let's see what that has to do with the last part of this question. So like we said, the EMF is a constant, so we can rewrite this expression as a VI relationship. So I rewrote the expression in this kind of sort of strange way, but really what I'm trying to do here is make the equation of a line. So if I were to graph this, we end up that the slope is equal to negative the internal resistance. I'm not happy about the negative there. But I'm kind of looking at the mark scheme, and I'm actually writing more than the mark scheme requires. Mark scheme says variable resistor would allow for more readings to be made, and the gradient of the VI graph could be found to give R, which is what I'm saying. But that's actually how it would be done. And they said you would get 1 out of 2 points just simply for saying that if you collected more data, then you would get 1 out of 2. But it's the second point is talking about the slope of voltage versus current. So yeah, variable resistance allows for multiple resistance values and thus multiple terminal voltage values. And by having multiple terminal voltage values, there's going to be current values to go with that. And then if you were to plot voltage versus current, you could get the internal resistance from the slope of that graph. So the 2 points here are the multiple R values. Having a variable resistor allows for multiple R values. And then the second point is the point about the slope. And that was the last question for number 2. I believe it says turnover. Yeah, section B. So that's it for, what test is this? That would be May 2018, time zone 1, paper 3, section A. Thank you.